exothermic and endothermic reactions throughout the remainder of our life in organic chemistry. Matter of fact, we're going to derive tremendous predictive power from these two concepts. Exothermicity and endothermicity, sort of the same concept, one backwards of the other. And in order to do that, we also need to consider another energy term called entropy. Now, entropy is simply molecular disorder or randomness. It's most accurate to consider entropy as the number of states that a system can access, right? So oftentimes we'll use the analogy of flipping a coin. If you have 4 coins, how many states can we have such that all 4 coins have heads up, right? If we're going to flip a coins, four coins, in how many states is it possible that they're all heads up? Well, only one state, right? There's only one condition in which they're all heads up, and that's if they're all heads up. However, if 1 is heads up and 3 are tails, then we can see that there's 4 possible states, right? So the number of states goes up depending on depending on the situation, right? So if we have in our textbook, in the Klein textbook on page 231, he uses 4 coins and he says, what if 2 are heads up? And he has a good figure, I think, here, which shows that there are 6 possible states, right? So entropy is the number of possible states that a system can access. That'll make more sense as time goes on, but in the interim, actually, we're never really going to need to get too deep into it. In organic chemistry, we can simply say entropy is the degree of disorder or the degree of randomness. So another example that he gives is here, and he talks about if you have 2 vessels where it's closed off, right? You've got 2 vessels, one's empty and one's got some gas in it. Well, each of these little spheres represents a particle of gas. If you open this up, then the gas is going to go into both vessels, right? And it's actually going to even out. And the reason why is because that gives each particle more area to probe, right? So more volume for the gas to occupy means greater entropy. And so volume is an issue with respect to entropy. And the other issue, more commonly, I think we're going to see in organic chemistry reactions is something like this. If you have 1 mole of reactant and you go to 2 moles of products, then we have a greater entropy. All right, and it has to do sort of with where A and B can be with respect to each other and so on. So 1 mole of reactants to 2 moles of products is an increase in entropy. And another increase in entropy is if you have a cyclic compound and you break it, you break that XY bond, then, and this makes, I think, a lot of sense too, that if you break it, then these X's and Y's are not tied to each other and they can sort of flop all around in space, right? So again, if you can think of entropy as the more possible states, the greater entropy is more possible states for a system to probe. Okay? And I think that is going to be a decent foundation for how we're going to use entropy in organic chemistry.